Alright, way back in an earlier unit, we learned about naming acids, how to recognize the formula for an acid, and in a unit that followed that, but still before this one, we learned about net ionic equations and complete ionic equations, and we're about to use all of that again. What we're going to deal with first is the theory of acids. Now, there are several different theories of acids. The one that we've been using so far is the Arrhenius theory. I should say the Arrhenius theory of acids and bases. The Arrhenius theory states that acids are any substance that donates a hydrogen ion to water. And the Arrhenius theory also states that an Arrhenius base is any substance that donates a hydroxide ion to water. So, if I have something like hydrochloric acid, so in the Arrhenius theory, if we take something like hydrogen chloride, which in its pure state is a gas, and then we dissolve it in water, and the way we might show it being dissolved in water is over the arrow showing going from reactants to products, we put water here. And this would be a way of indicating we are doing this reaction in water, in a water environment. What happens is it breaks up into hydrogen ions, and those hydrogen ions are dissolved in the water, so we call them aqueous. And chloride ions, which are aqueous. And that looks a lot like how we learn to create acid or ionic formulas in the first place. Only we started with the two ions and we made them into some kind of a formula here. Found a balanced formula. And then when we got to net and complete ionic equations, we took that same process and undid it. We started with the formula and broke it up. Well, so the hydrochloric acid actually breaks up into these. Now, the way we'd actually write that would be to go ahead and show the hydrogen chloride dissolved in water. So we'd show it aqueous, and we'd show that it breaks up into hydrogen ions and chloride ions. It's important to remember that hydrogen ions are protons, because a hydrogen atom, if you recall, has only one proton and one electron. To get this positive charge here, you have to get rid of an electron. So if I only had a proton and an electron to start with, and I get rid of the electron, all that's left is a proton. So we often call this a proton. And we call the removal of a proton deprotonization. Deprotonization. Okay? So that's the Arrhenius theory for acids. Remember, an Arrhenius base is one in which we break up something and form hydroxide ions. Okay? I'm not going to get to that right now. We'll do that a little later. Then there is an alternative theory of acids and bases which actually cover more substances. There are substances that behave like acids and do the kind of work an acid does, but wouldn't look like an acid under the Arrhenius theory of acids. And so for that, we're going to use what's called the Bronsted-Lowry theory. Okay, now these are two different people, and that O does have a slash through it because it's a language that isn't English. It's something that has this kind of letter in it. And the Bronsted-Lowry theory, it's not enough that we're taking a hydrogen ion and just simply putting it in water, dissolving it in water. That hydrogen actually goes along and bonds with something else. Usually that's water. Not always. It can bond with anything. If you can take a hydrogen from someplace and put it on something else, that's a Bronsted-Lowry acid, regardless of whether it's water. But a lot of the time what we're talking about when we're dissolving the acid in water is the hydrogen ion actually joins up with the water. It's kind of the same process, but a little more involved. So in the Bronsted-Lowry theory, we would take the hydrogen chloride, and we'd take the hydrogen off of this and join it up with a water molecule. So a hydrogen, just like this, a hydrogen comes off of here and joins up with the water molecule. Now if we've got 3 hydrogens then, that's H3O. And when a hydrogen comes off of an acid, it's a proton. It has a positive charge. So if a positive charged particle comes off of here and joins up with a neutral particle, the resulting particle has to have that positive charge. If we take that hydrogen off of this, what remains is the same thing that remains up here. So this would be a way of describing or illustrating the deprotonization of hydrogen chloride, hydrochloric acid, using the Bronsted-Lowry theory of acids. Excuse me. Okay? Either way, we get one of these particles or one of those particles. This is the particle from which we originally got the pH symbol. Okay? It's the proton or the hydrogen ion that is the H in pH. The P means negative logarithm of something. So if you get your calculator out and look on the keyboard, if you have a scientific calculator, you're going to have a logarithm button someplace. Excuse me. On this calculator, it's right here. Your calculator may have a logarithm button in a different place. Here's another calculator. In this case, the logarithm button is in blue above the 10 to the exponent button. So I'd have to hit Control and then the 10 to the exponent button in order to use logarithm. Here's another calculator. Let's see if I can find the logarithm button. There's the logarithm button right there. Okay. So every calculator has it set up slightly differently. I've got an odd sort of calculator. Okay, here's one. There's the logarithm button. So it should be somewhere on the calculator. You should be able to find it on your own, but you have to learn how to use it on your calculator. Now the lesser expensive or the least expensive calculators are the ones that are the hardest to use to calculate logarithms, or for that matter to undo them. Then the H part of the pH, in the pH, actually means the hydrogen ion concentration. Okay? And that's the molar concentration. And we'll talk about that in a minute. Now, in the Arrhenius theory, it'd be the concentration of the proton. Okay? In the Bronsted-Lowry theory, since the proton goes and joins up with the water and forms this, in the Bronsted-Lowry theory, it's actually this. Now, let's talk about all of this theory and tying it in with the concentration. Okay? Because the H here really isn't just the H, but it's the molar concentration of H, which means the molar concentration of this or the molar concentration of this. The way we symbolize molar concentration is, for any species, is to put that species in brackets. So when I say molar concentration of sodium chloride, I could just as easily write that in this manner. This means to a chemist the molar concentration of sodium chloride. So if I want to know the molar concentration of hydrochloric acid, I write it like this. This is the molar concentration of hydrochloric acid, or the molarity of hydrochloric acid. Now remember, the pH isn't so much concerned about the concentration of the acid here or here. The pH is actually a measure of the hydrogen ion, or the concentration of this. By the way, this has a special name. We've learned it previously in an earlier unit. It's called hydronium. Okay, so this is called hydrogen ion or proton. This is called hydronium. Okay? Well, the molar concentration of this turns out to be the same molar concentration as that. Now here's why. Moles are the number of particles grouped together in 6.02 times 10 to the 23rd groups, or particles. Remember, a mole of anything is 6.02 times 10 to the 23rd of anything. And that's one mole. Like a dozen is 12. A mole is 6.02 times 10 to the 23rd of something. If I have 6.02 times 10 to the 23rd of these HCl particles, and one hydrogen from that breaks off and joins up with 6.02 times 10 to the 23rd water molecules, I form 6.02 times 10 to the 23rd particles of hydronium. So 1 mole of this acid will make 1 mole of hydronium. If we do all this in 1 liter of water, for molarity, I can find my notes for molarity here. Molarity is moles of solute dissolved in a liter of solution. If I take a mole of this stuff and put it in a liter of water, and say we have a liter of water, we dissolve this in the water, we're going to get a liter of this. We're going to get a mole of this, rather, in that liter. Okay? So a molar concentration of hydrochloric acid will result in 1 molar concentration of hydronium. Or, if we're using the Arrhenius theory, 1 molar concentration, 1 mole, 6.02 times 10 to the 23rd of these particles dissolved in water will give us 1 mole of this in that same amount of water, because the whole thing's taking place in a liter of water. So we get a mole or a molar concentration of this. Okay? So there's a 1 molar concentration of this, we'll get 1 molar concentration of that. 1 molar concentration of this, we'll get 1 molar concentration of this. Or 1 molarity of this will give you 1 molarity of this. Now it's really important that you remember this only applies to strong acids. In our previous lab, we found out hydrochloric acid was a strong acid. It doesn't work for weak acids, and we talked about the theory of that earlier. It works for strong acids as long as there's only 1 of these hydrogen ions to be pulled off. 1 hydrogen ion to be pulled off. Something different happens if there's more than 1 hydrogen ion. We're going to stick with, right now at least, 1 hydrogen ion on a strong acid. Okay? Alright, so then, all of that together means this, in terms of calculating molar concentration and then calculating the pH. If 2.50 grams of, let's just say, hydrochloric acid, in 5 liters of aqueous solution, which means the hydrochloric acid has been dissolved in water. Aqueous means dissolved in water. Okay, if that much HCl is dissolved in 5 liters of aqueous solution, what's the pH? Well, pH is based on molar concentration, and molar concentration is moles of this stuff over 1 liter of this stuff, of the aqueous solution. So, we're going to start with 2.50 grams of HCl. We're going to find the molar mass of HCl. These are the atomic masses of hydrogen and chlorine. There's only one hydrogen in the formula and one chlorine in the formula. Molar mass is by definition the sum of all the atomic masses of all the atoms in a formula. And so what we're going to do now is to add up the sum if I can get my calculator to do what I want it to do. Here we go. Okay. I'm going to add up the sum of all the atomic masses of all the atoms in this formula, HCl. Two empty slots, 2 insignificant digits. This is grams of HCl. We're going to round this off now. And we get 36.461 grams of HCl equals 1 mole HCl. With this equality statement then, we can convert this into moles by putting this side of the equality statement on the bottom. The other side of the equality statement goes on the top. 2 things that are equal, putting a fraction equals 1. We're changing the value without changing the actual amount. Cancel units and species the same way you cancel x's and y's in algebra. We want to put the moles of HCl then over the liters of solution. Okay, by putting this in a fraction underneath the 1, when I multiply these together, I'll get moles of HCl over liters of solution, which will give me the molarity. And that's moles of HCl, that's what we have left on the top here, over liters of HCl solution on the bottom. We're going to round that off to these 2 numbers, measured and calculated numbers. There's 3 measured or calculated numbers, this, and this. Of those 3, this one and this one have the least digits. That's how many digits we want in our final answer. Leading to zeros are not significant. 1, 2, 3. underline everything else, draw an arrow, and this is going to give us the molar concentration. All right? Since this is a strong acid, since it only has one hydrogen to be given away, then and only then, because it's a strong acid, because it only has one hydrogen to be given away, the molar concentration of HCl will be the same molar concentration as the hydrogen ion and will be the same molar concentration as the hydronium ion. Only because it's a strong acid and it only has one proton to be given away. Therefore, the pH of this HCl solution is the negative log of the molar concentration of this or this. It doesn't matter really which one you're using. Okay? And that concentration is this. Okay? This just happens to be equal to, or actually no, it's not equal to, but it means that you have 0.0137 molar hydronium ion. Only because it's a strong acid, only because it gives away one proton. Okay? So now we can take the negative log of this. That number there. So that's the negative log of 0.0137. Now, you have to be careful. Some calculators will let you put it in just exactly like this. Some calculators require you to put in this number, then log, then change the sign. You have to figure out how to make your calculator talk the language you want it to talk. Or, right, really what you're doing is learning to speak your calculator's language. Okay? The more expensive the calculator, the easier it is to calculate pH. Okay? So, let's see here. I'm going to put it, with this calculator, I can put it exactly like it looks. I'm going to do the change of sign button first. I'm going to do control, logarithm button. Now, on these more expensive calculators, the reason you've got this little place down here at the bottom, I don't know if you can tell what that is, but it says logarithm, and it's got a box down here. It's asking for the base. The base here is a base of 10. Okay? If we're using any other base, we put a different number there. So this is the base of 10. All the pH calculations we do are on a base of 10, meaning you have a 10 to some exponent. If we were writing this number as an exponent, we could write it as 1.37 times 10, move the decimal place 2 places, negative 2 molar HCl. Okay? So the base here is 10. And LOG, this kind of logarithm, is on a base of 10. So we're going to put in base 10, 0.0137, hit enter, and I'm going to get this pH, 1.86 and so forth. So the pH is equal to that. Now, there actually is a third rounding system for logarithms and exponents. We're not going to get into that. I'm just going to expect you to use the same rounding system as you learned to use in multiplication division. So since this number had 3 significant digits, we're going to put this. We're going to write this answer in 3 significant digits. So our pH will be rounded off to 1.86 for this solution. Okay. All right. If you want another pH, and you have a strong acid with only one proton, one hydrogen ion on the front. First you calculate what the moles are going to be. Then you calculate what the molarity is going to be. Then you take the logarithm, and then you take the negative, or the change of sign of that logarithm. Okay, if I were to take the logarithm of this number, I get negative 1.86. And I just change the sign to get positive 1.86. Try it on your calculator if you want to. Alright, it's that simple. Find the molarity. Molarity is moles of whatever the acid you're dissolving. You want to make sure you have the molarity of the hydrogen ion of the hydronium. Then you find the negative logarithm of that. Now you're going to have to work with your calculator a little bit to figure out how to make it work. And for some of you, it may be a little bit difficult, but you've got to play with it until you get it. Hopefully there are study partners or problem-solving partners in this class that can help you figure it out. Learning partners in this class that can help you figure out how to make your calculator do it. If you're going to use one of the least expensive calculators, you're going to have trouble. But if you'll use a pretty good scientific calculator, and calculators like this only cost about $12 maybe, okay? It's pretty easy to get those to give you the right answer. So let's do that now. Let's do a problem in which you calculate the pH of a solution if you know what's going into that solution. Okay? So here's your second practice problem. You have 3.7 grams of hydroiodic acid is dissolved in 25.00 liters of aqueous solution . What would you expect the pH to be? Alright, and then we'll do a homework problem too. You have 2.00 grams of hydrochloric acid is dissolved in 10.00 grams of aqueous solution . What would you expect the pH to be? Alright, if you've solved the problem correctly, you should get a pH of 2.93. The complete solution is you start with 3.75 grams of HI, and you're going to calculate the molar concentration, which we can also call the molarity of the HI solution. You first determine the molar mass. We've calculated molar mass many times. There's no reason to round up here because there are no empty slots to the right. So this is the mass of HI, hydroiodic acid, in 1 mole of hydroiodic acid. And we can take this value, grams of HI, 4 grams of HI, and put it on the bottom of a fraction. this value, the 1 mole, and put it on the top. Cancel units and species like you do in x's and like you do x's and y's in algebra. Divide by the volume. That will give us the moles of HI over the liters of solution. Moles of HI over liters of solution is molarity, or the molar concentration. The value, numeric value you get is this. You may have a few digits over here that are less. Don't worry about it. You round it off, you get this, and this is your answer. Round it off properly. This is the correct answer. 0.00117 molar HI solution. The answer to this part of the problem anyway. Once we get here, we're not quite done. This is the molar concentration. Since hydroiodic acid is a strong acid and it has only one proton, HI has only one H on the front to come off in solution, one proton to give away, as seen in the chemical equation below. Actually, I didn't write it out, so let's write it out here. HI, we're going to put it with a water molecule. We're going to use the Bronsted-Lowry equation. The hydrogen ion comes off and joins up with the water. You take, the water can be written as HOH, so we take one hydrogen off. What we have left is hydroxide ions. Take the hydrogen off, put it on here, leaves you with OH, okay? And so the number of particles of this equals the number of particles of this because it's a 1-to-1 ratio. If you balance the equation, it's going to be equal on both sides. So therefore, the number of moles of this will equal the number of moles of that. Therefore, the molarity of this equals the molarity of the acid itself. The molarity of the acid was this, so the molarity is going to be the same here for the hydronium. pH is the negative log of the hydronium ion concentration. Negative log of that gives you this number. Okay?